Hey guys, welcome to yet another sensors video. This time we're looking at the Rotary Encoder. This is a cool little device. Here's the one that we have in the lab. It is specifically ACZ16 from CUI devices. Who knows? There's thousands of different kinds of rotary encoders. The most common form that we find these is actually built into a lot of our motors that we use in FTC. So somewhere within the housing of that motor is a rotary encoder, and we don't have to do any circuitry work. We can usually just plug those in and get some information. But for today, we're going to look at the raw device itself. We have to do a little bit of breadboarding to get some useful signal out of it, and we'll see what it looks like on the Arduino. So what is a rotary encoder for? Well, as the name implies, rotary, meaning rotation or spinning. It's a way of understanding rotational motion and encoding that into some kind of useful signal. And so in the case of a rotary encoder, what we get is some signal every fraction of a turn. And with this encoder in particular, we get a signal 24 times per rotation. So it's about 15 degrees, which is fine enough resolution for a lot of things, especially when we're thinking about spinning and measuring speed. That's plenty of information to find out how fast a motor is turning or find out how quickly a wheel is moving. So let's take a look at the data sheet, see what we can figure out about this. We'll do a little bit of breadboarding, hook it up to the Arduino, and see what we can do in terms of measuring rotation. Here's the data sheet for our specific one. If we get different kinds, we would look up the data sheets for those. But the thing that we're really looking for here is this circuit diagram, this suggested filter. This gives us a bit of a hint of how we could hook this up and get some useful signals out of it. It might look like a lot, but it's very simple. I'll break it down for you here. Inside this dotted line, this is the encoder itself, and it has 3 pins. And you'll notice on ours, there's those 3 pins. And I've got just some jumpers hooked up to it to connect to the breadboard. One of those pins is going to go straight to ground. That's apparently terminal C. The other 2 have identical circuits on them. They've got a resistor up to 5 volts and a resistor over to here, which will be the signal. And at the same place here, they've also got a capacitor to ground. And they suggest 10,000 ohm resistors here, 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 and here, and 0.01 microfarad capacitors here and here. Just some kind of small capacitor will do the trick. The exact value doesn't really matter. One last thing we need to find out on this data sheet is which of the 3 terminals are A, B, and C. We need to make sure we connect those correctly. By the naming of it, we might expect that terminal C is one of the outside ones, but which way is left or right, who knows? By this diagram, it might look like it's the middle one, but let's make sure before we hook anything up. Down below, here's a mechanical drawing, and yeah, it looks like it does have them labeled. So if we take a look at this drawing, so this is front full on. If we turn to the side, that's this one. So if we turn it backwards, then that must be this one. So by my reading of this, if I'm looking at the back, A is the one on the left, B is the one in the middle, and C is the one on the right. So it's this one on the right here that we want to hook directly to ground. And then A and B, it actually doesn't matter which one is which, but those are the ones we're going to hook up to that resistor and capacitor circuitry. And what that circuitry does is not only give us a power and ground to reference, but the capacitor helps filter the signal so it's not noisy, there's not jitteriness or waviness. It's holding consistently to one value. So here I've gone ahead and built this circuit on the breadboard. These 3 jumpers are the jumpers coming from the encoder. This brown one on the bottom is the one connected to what we saw was pin C, which was the one on the right looking from the back. And then the other 2 pins, A and B, I've connected into the breadboard here and here. Elsewhere on the breadboard, I do have 5 volts and ground coming in from the Arduino to power this. But we'll just see that I've made this circuit very visually the same as that circuit diagram. You don't need to do this, but it helps with understanding things. You can make this a lot more compact and condensed. But we'll see here is from that signal a resistor up to 5 volts, and as well a resistor out to here. This would be where the actual signal out that we would read is on this row. And we've also got this capacitor here down to ground, and that's helping to stabilize that signal. Now, without plugging this into the Arduino, nothing's happening. I can turn this encoder as much as I want, and we won't see anything. But to make things a little bit visual, let's just hook up a LED and resistor here to this output and see what's going on. So from that output, a little current limiting resistor for our LED, and then the LED to ground. So we see the LED turn on. I'm not touching the encoder right now, so the LED is not doing anything at all. But as I start to turn this encoder, we will notice, ooh, it flickers. So I got to go really slowly, and let's see what happens. If I just start to turn it, it turns off, and I turn it a little bit further, and it comes back on. And this encoder is nice because it has what's called detents, which means it kind of snaps into position every fraction of a rotation. So every 15 degrees, this thing kind of clicks into place. And so I can notice as I click it from one place to the next, I get one of those flickers. Halfway through that position, the light turns off. And then when I get to the end stop, the light turns back on. So this is pretty handy. What this is telling us is if we can just measure the voltage here at this signal output and record that in the Arduino, we could count how many times this signal is turning off and then on again. And that will tell us how many steps of 15 degrees we've rotated this axle. And you could imagine this axle here being connected to the shaft of a wheel or a motor, and you could be measuring the rotation of that. So let's see how that would look in the Arduino, and we'll talk about the limitations of this. The first thing I have to do though, I'm going to unplug the LED and connect in a jumper from the Arduino. This is right now connected to pin 2 on the Arduino. Because we're using serial communications, we'll remember that we can't use pin 0 and 1. So we'll start at pin 2 and we'll take a look at this. You'll notice also right now I'm not using the other signal, this red wire that has its own filter circuit. We'll see what that's for in a little bit, but first let's check out this initial signal. So here we are in the Arduino IDE, and let's take a look at how we could write some code to detect these turns, these fractions of turns in the rotary encoder. You'll notice I already start with some of the boilerplate, some of the generic stuff. We've got pin mode 2 set as an input because we want to be measuring the voltage on that pin, and we're starting serial communication. Let's think about what we want to do here. We need to be keeping track of when that pin changes voltage. It starts high and then dips low and comes back on high again. And each time that happens, we want to say, hey, we've moved a step. So to start off, let's just make sure that we're actually getting the signal into the Arduino in the first place. We'll do that very simply by going serial.println, and then we'll just use digital read and pin 2. So whatever the value on pin 2 is, we're going to read it and just print it directly to the serial monitor. So let's upload this to the Arduino and take a look at our serial monitor. And just like before with the LED, we see when I'm not touching it, we're just getting all ones. But as I start to rotate this, I'll try and go very slowly, and we'll see it dips down to 0 and then snaps back up to 1 for every tick in that detent. So what we would like to do is track this. Whenever one of these events happens, let's increment a number and let's just print that number. We don't actually care about the current state of this signal. What we care about is how many times that pulse has happened. So how can we do that in code? Let's take a quick look. To start off with, let's make a variable. It'll be an integer. We'll call it ticks. I'm just using ticks to refer to those clicks, those 24 clicks per rotation. And so we'll start it off at 0. This will be our counter that keeps track of whether or not we've clicked. We've got a few choices here. We could either choose to detect when that signal goes from high to low or from low to high. It doesn't actually matter which one we do. We could actually use both and get even finer resolution, but for the purposes of this, let's worry about just one of those. Just because intuitively it makes a little bit more sense, let's track that signal when it comes back up from 0. So it dips down to 0. We want to know when does it come up back to 1. So what we need to know is the last time we checked, was it 0, and is it now 1? If it was 1 the last time we checked and is still 1, we don't care. If it was 1 the last time we checked and it is now 0, we don't care. The only time we care is if it used to be off and now it's on. So we need some way of preserving the previous state of this signal. So we'll make another variable here. We'll call it previous state or prev state, whatever. Maybe we'll set it to 1 initially because we do know that it will start off at 1. And now let's get rid of this print line for now. We'll print something else in a sec. What we want to do is every time through the loop, we want to have a variable. We'll call it new state. That's the current state, whatever it is now. And we'll set that equal to digital read pin 2. So whatever state that pin is currently at, let's store that in a variable. Now we want to ask ourselves two things. Is that new state a 1? And did it used to be a 0? So we'll say if new state equals 1. And we can do this one of two ways. I'll show you both. We can say and. So 2 ampersands is the operator for logical and. So if new state equals 1 and previous state equals 0, this is when we want to do the stuff. Another way of writing this same logic, we can split this up into 2 if statements. We can say if new state equals 1, and then inside of that if statement, if previous state equals 0, and then another set of brackets. So we have this nested if. Functionally, this is identical. For clarity's sake, I'll do it this way. And now we just have to figure out what we want to do here. So if this has happened, if we've gotten to this state where the signal is currently on and it used to be off, what do we want to do? We want to increment our counter. We want to go up by 1. So we can say ticks equals whatever ticks currently is plus 1. Take whatever value is currently stored in ticks, add 1 to it, and store that value back in ticks. And a simple way of doing this, rather than writing this whole thing out, we can actually just say ticks plus equals 1. And that does exactly the same thing. This is a special operator, plus equals. You can do the same thing with minus equals, times equals, whatever. And it basically takes the value in that variable, does that operation on it, and then stores the result back in the same variable. One last way we can do this is we can just say ticks plus plus, which is specifically for incrementing by 1. Just to make things clear though, I'll just say ticks equals ticks plus 1, just so it's obvious what's going on there. And then I think every time that we do this, we should also print it to the serial monitor, and we'll just print the new value of ticks. So we'll only be printing the value of ticks when it changes rather than every single frame. The very last thing we have to do is we have to make sure that we update our previous state variable. So we can say previous state should now equal new state, so that we're ready for the next time through the loop where we will read in the new value and put the new value in new state. We need to know what it was during this frame. So with this code, we should be able to see that ticks counter incrementing every time we rotate the encoder 1/24th of a turn, or whatever the signal resolution is on the specific encoder that you have. So we'll upload that code, open up our serial monitor, and take a look and see what's happening. So it's blank because I'm not moving this, but if I start to turn it, I'll move it 1 tick over. We see a 1. If I do it again, a 2, a 3, 4, 5, and I can spin this quite fast and it'll pick those up. At a certain speed, you will stop keeping track of it because some of those pulses will happen in between frames of the Arduino. And there is a way around it. It's using something called interrupts, which basically tells the Arduino to run a function anytime it detects some electrical signal, regardless of what the rest of the code is doing. That's a more advanced topic. We don't need it for this very simple exploration, but know that there is a way to handle that. If this is spinning really fast, we will start losing some of that information. Now, one thing to note, I've been turning this counterclockwise this whole time, but watch what happens. So I turn it counterclockwise and it goes up. And if I start turning it clockwise, we still go up every tick, right? Because this signal is doing that low pulse every time that this shaft turns 15 degrees, but it doesn't care which way it's turning. It just dips it low and dips it high in between those detent positions. So this might be useful in some applications, but for the most part, it's not terribly useful to know just if it's turning. We would like to know which way it's turning. We would love to be able to keep track of speed or position and know that, okay, we've turned 4 forwards and then 2 back, so we've actually only turned 2 forwards. And that's where that second signal comes into play. So we're going to take a quick look back on the breadboard and see what that second signal does and how it differs from the first one. So to start off with, I'm just putting back this LED so that things are nice and visual for our first signal that we were looking at. And we'll just make sure that as I turn this, we do still get that flickering, that low pulse every detent. But now let's hook up another LED and resistor to the second signal and see what happens there. So we can see that I have both LEDs are on. So it looks like the signal's the same, but I'll start turning this and we'll see what happens. I have to go really slow for you to see this. I'm going to start turning. So they both turn off, but as I keep going, the one on the right turns back on first, and then the one on the left. And this happens every time. I keep going, and the one on the right comes back on, and then the one on the left. And this is when I'm turning it counterclockwise. So what do we know? If I'm turning this counterclockwise, and the one on the right has gone from 0 to 1, and the one on the left is still off, we know that we're going counterclockwise. Now, if I go the other way, if the right one goes from 0 to 1, and the left one is on, that means we've just gone clockwise. So we can now detect forwards or backwards using the combination of the two because their signals are offset. And we can take a quick look at the datasheet here and see that in these waveforms that they've put in. Now it's a little bit off because it was looking like they were actually turning off at the same time. I think it's just because I'm not able to go as slowly as I would need to just with my fingers. But the key is that we have these two waveforms that are just slightly offset from each other. And so by understanding that pattern, we can tell if we're going clockwise or counterclockwise. So let's implement that logic in the Arduino and see what that code looks like. Before we get to that, I'm just going to make sure we've got our signal wires connected. We'll remove these LEDs. We'll still have pin 2 going into this original one. And we'll use this yellow wires going to pin 3 on my Arduino. So now let's take a look at the code. First couple obvious things we need to do is we need to set the pin mode for pin 3. This is also an input. And then everything else we need to do is just going to be down here in the loop. Now, because we were talking mostly about the change in the right LED just now, we'll change this to digital read 2 for the new state. So this is the main state we're going to keep track of. And we still care about if it was 0 and is now 1. But now we need to add a little bit more logic inside here to figure out if we're going clockwise or counterclockwise. So what we said was if the left signal was still off when the right signal went from 0 to 1, that meant we were going counterclockwise. So we can say here, let's make another variable for holding the state of the left signal. And that's digital read 2. And so what we want to know is if the left state is 0 at this time. Remember, we're inside this if statement. So we already know the one on the right has gone from 0 to 1. So now we want to check if the left statement is off. That means we've gone counterclockwise. Counterclockwise, CCW. This comment here is just, then what do we want to do? Let's take away 1 from the ticks, and that will represent counterclockwise motion. And so we can say ticks equals ticks minus 1. We could also say ticks minus equals 1 or ticks minus minus, either way. And then we could also do another if here and say if left state is 1, do the clockwise thing, which would be ticks equals ticks plus 1. But we can actually save ourselves a little bit of time because there's only 2 cases, either left state is 0 or left state is 1. So we can remove this extra if and replace it with an else. And we'll remember that else always has to come after an if, and all it does is handle the other case when this isn't true. And it looks like we have 1 extra bracket in here for some reason, so we'll get rid of that. And then the last piece is we'll remember to still print out the value of ticks. And I'm going to put this here outside of this if of checking if we're going clockwise or counterclockwise, because we want to print the value either way. And I don't want to have to write this line twice. I could put this line in here and in here, but I don't want to bother doing that. That's extra work. Okay, so here is we have detected some rotation, but we don't know which way yet. So we're going to find out what value that other signal is at, and based on that, we'll know if we're going counterclockwise or going clockwise. and adjust the ticks variable appropriately, and then we'll still just print that out. So let's see what this looks like in the serial monitor and see if we've got it working. So let's make sure to upload this first and check it out on the serial monitor and see if it is working. So we are getting no messages yet, which is fine because I haven't started turning this. So I'll start by turning this clockwise. And what we are expecting is positive numbers. We're going up 1, 2, 3, 4. And now if I turn it counterclockwise, we should see it counting down. And in fact, it will start counting into the negatives because we're storing integer numbers. But if I turn it backwards and now I turn it forwards, we go up and we go back down and we go up and down. And this is perfect. And now I'm keeping track of my rotational motion forwards and backwards using this rotary encoder. And again, these are those fractions of a turn. We could do some math with this number and turn it into actual rotations, or we could use that along with the time and turn that into speed. But for this exercise, this is all we needed to do. So there you go. That's how an encoder works. In terms of the vocabulary of this course, we would still call this a passive sensor because we're not sending any data to it. We're really just hooking it up to power and seeing what happens. But this is a very, very, very useful piece of technology in the robotics world where we want to keep track of rotation. And usually when that's continuous rotation, we can't use a potentiometer. So we use an encoder. And this gives us the ability to track rotation of wheels and motors and belts and all sorts of things with a high degree of accuracy so we can know exactly where things are positioned. This is very important in FTC and other robotics competitions, especially with autonomous modes, for keeping track of how far things have moved. And this exact same logic that we see here with these two waveforms that are doing the same pulses but just slightly offset is exactly the same kind of signal that we see out of the encoders built into a lot of the motors that we have in the lab. So I hope you found that pretty cool. I know you don't have these encoders yourself, so you can't build this yourself, but you can at least write about it, and the next time we're in the lab, you can tinker around with this and see how this works and get something interesting working with an encoder system. We've got one last sensor, or I guess pair of sensors to look at, and that is the thermistor as well as the photoresistor. These are essentially the same thing, so we'll cover them in one video. It'll be very quick and straightforward, and then you have all the information you need to finish that sensors research project, turn it in, get that credit, and move on. So take it easy, have a good one, and catch you later.